Good day to you. There are many physical phenomena in nature that can be represented as waves, and in order to understand them we have to develop a vocabulary that we can use to be able to talk about their various properties and how to measure them, and the kinds of phenomena that wave phenomena not only are, but the wave phenomena can drive as well. So let's start with a very simple example of what a wave is. It's a very intuitive example, and that is the kind of wave that results from a sound that is being generated by some kind of object in nature. So if we come to a sound source, let's say it's a speaker of some sort, and that speaker has a cone that's moving back and forth. That speaker is going to generate a series of sound waves that are going to be propagated away from the speaker at a certain velocity. And these are going to be intercepted by some kind of an individual that has an ear over here. Okay? And when that person hears the sound, that person is hearing an oscillation of pressure that's generated by the sound generator over here. If you look at the pressure at the various parts of the sound wave, there are areas of high pressure where the speaker cone has been forced out, and these are interspersed with periods of low pressure as the speaker cone has drawn back. And if we have a little pressure device right here that can measure that pressure, what we will see is a waveform that looks something like this. It's a nice sine wave sort of a form. So this is going to be the pressure that is measured at the point of the ear. Now, the main thing about this pressure is that it oscillates back and forth around some kind of a mean, and it has certain properties to it that are important to be able to quantify, so that we can talk about the kinds of phenomena that variation of pressure is driving. The first thing that we want to look at is the distance between similar parts in the wave. If we come over here, we're really looking at this distance right here, the distance between peaks of sound pressure. We could just as easily look at the distance between troughs of sound pressure, but this distance right here corresponds to a property that we call the wavelength. And the wavelength is usually abbreviated with a Greek letter lambda, which looks in lowercase like this. Now, we also, in order to be able to fully characterize the sound wave, we have to be able to quantify a couple of other properties. First is that there's going to be a certain speed with which those waves propagate away from the speaker, and we can refer to this as a V. And therefore, if we come back and measure the pressure at our ear, this V is going to translate into a certain time signature. That is, there's going to be a certain time that will be required for the pressure to go from one peak to the next peak. So if we wanted to build a representation of what was happening with the wave itself, with time the wave is actually moving forward in space over a certain period, and so that it will take a certain amount of time for the high pressure being measured at the ear, it will take a certain amount of time for the next wave of high pressure to reach the ear, and that time is going to be related to the speed with which those waves are propagating. Now, because the speed is going to be determined by such things as the medium or the nature of the wave phenomenon going on there, we can refer to another property of waves that is important to understand, and that is the frequency with which these troughs migrate past this fixed point over here. And so what we have here, when we talk about waves, we're talking about three fundamental properties, quantities that we need to be able to quantify. One is the lambda, or the wavelength, the distance between similar parts of the wave, and this has units of meters per wave. Okay. We also have the speed with which a wave can propagate, and that is going to be v. That's the speed of propagation. And that is going to have units of meters per second. And then finally we have this, this other quantity that's related to the two, the frequency of propagation. And this has the dimensions of waves per second. That is, how many waves per second will go past this fixed point. Now, these three quantities are related by a fundamental formula, and that fundamental formula is very easy to understand. The frequency is equal to the speed over the wavelength. And if you work out the units of frequency, speed, and wavelength, you'll see that this turns out to be, these two are related to one another. V, for example, is meters per second. Wavelength is meters per wave. And if you work out the units, you'll see that the units come out to be waves per second for frequency, just as we said down here. Okay, so this is probably the fundamental relationship that describes how frequency, speed of propagation, and the wavelength are related to one another. Okay, now let's take some concrete examples of this and illustrate how these three properties interrelate to produce a phenomena that we sense and that we can characterize. And one we have already described, namely that of sound. Sound is a wave phenomenon. Sound is something that is carried by air. The sound is basically a property that can propagate in any kind of medium where there's some elasticity to the medium. And so sound is a property of propagation of pressure waves in elastic media. And in the case of air, the elasticity of the medium comes from the fact that you can compress, you can put pressure on a parcel of air, you can compress it, and when you release that pressure, that air will spring back to its original volume. That is, it has the same kind of elasticity that, say, a solid elastic material would. But you can just as easily refer to the elastic medium as being a solid, for example, steel or rock. All of those are elastic media, and it also can describe propagation of pressure waves in water as well. And that'll be especially important when we start talking about the phenomenon of hearing in the latter part of our course. Okay, let's take a look at how sound works. If you have sound, as we said, you have some kind of a device. We usually use a speaker that can oscillate back and forth like that. And when it oscillates forward, it generates a pressure wave that propagates forward in time. And when it pulls back, you have a suction on that. You're actually pulling back on the air, and that generates a trough of low pressure. And so sound is this alternating series of low and high pressure waves that propagate away from the sound source. Now, if you look at the kinds of speeds of sound that typically occur in different kinds of media, then they actually vary quite a bit depending upon what the elasticity of the medium is. If you look at the speed of sound in air, for example, then you'll find that the speed of sound there is on the order of about 300 meters per second or so. This is fairly slow compared to most other solids, but nevertheless it's fast enough so that we can hear sounds pretty quickly after they're generated. But of course, the further away you are from that source, the longer it will take to get there. That's why when you are watching a starting gun in a race, for example, you'll see the flash or the puff of smoke initially, but then it'll take maybe a half a second or so for the sound of the gun to get to you. If you look at very elastic media, like steel, then you're talking about propagation speeds that are much, much faster. This is because steel is a much more elastic medium. You can store much more energy in it as a result of its deformation. And if you look at the propagation speed, the speed of sound in steel, for example, you're talking about speeds of sound on the order of about 6,000 meters per second or so. And of course, sound can propagate in water as well, and that water is a bit less of an elastic medium than steel, but more elastic than air. And if you look at the propagation speeds of sound in water, you're talking about speeds on the order of about 1,500 meters per second. Okay, so speed of sound is a very, very important thing, and it depends upon the properties of the medium through which it's traveling. There are some other properties of sound that we need to pay attention to, though. And if we draw out a sound wave, again, keep in mind this is at a point where it's being measured or sensed, measured by a microphone or pressure sensor or sensed by an ear. And we can characterize the different properties there, the wavelength and, of course, the frequency and the period. And if these are going very, very fast, if the speed is going very, very fast, then irrespective of what the medium is, the frequency will remain the same. The only difference will be that depending upon the elasticity of the medium, the speed of propagation may be either higher or lower. And this ability to sense pressure variations, irrespective of the speed, is important for understanding how we can sense sound in the environment and the effects that sound has on other aspects of the environment. And so, independent of the medium, you have frequency and you have another property, the amplitude. And the amplitude and the frequency of the wave are two channels of information that can be picked up and sensed and interpreted in different ways. If you look at the frequency of the sound wave, which of course is related to its wavelength, then we perceive the variation of frequency of that wavelength as variation of pitch. And there's a range of frequencies over which we can sense a frequency of sound. We generally divide those up into three major categories. Infrasound, for example, is sound that is at very, very low frequencies below the audible range of sounds that we can pick up. And the range of frequencies of infrasound are on the order of less than 20 cycles per second. Cycles per second is our unit of frequency. The unit that's attached to that is the hertz, or Hz. And when you are talking about infrasound, you're talking about frequencies that are less than 20 hertz or so. If you look at sounds that are above our range of hearing, these are called ultrasound, and these are sounds in which the frequency is greater than 20 kilohertz or so. And in between, of course, is the range of audible sounds, and this is from 20 hertz to about 20 kilohertz or so. These are the sounds that we can hear. And our perception of variation of frequency in this case, of course, is pitch or tone of the sound. When you're dealing with sounds down close to the infrasound range, that is low frequency sounds, then this corresponds to a deep tone. As you go up towards the high end of the range, that is up towards 20 kilohertz, you're talking about sounds that are high pitched, up towards the right end of the piano. And so frequency can be interpreted and can be sensed, that doesn't tell us anything about what's happening with the other aspect of waves, though, and that is this amplitude here. And keep in mind that we're measuring here a variation of pressure in the case of sound, and the amplitude then is an indication of the magnitude of the pressure fluctuations about the mean. And when we talk about amplitude of sound, for example, we interpret that as loudness. So you can have both soft, high-pitched sounds or loud, high-pitched sounds. Amplitude is a channel of information waves that is independent from the frequency. Okay, so that is sound. Now, sound is a phenomenon specifically of propagation of energy through elastic media. But in the physics of life, though, there's one other major aspect of energy flow that can be characterized in part by a wave type of phenomenon. Not completely, but of course that wave type phenomenon is light. And we'll have more to say about the generation of light and what it means in another module. But for now, let's just concentrate on how we can characterize light as a wave phenomenon and how we interpret that with our own senses. Now, light is a form of electromagnetic radiation. It is not a mechanical propagation of energy as sound is. There's some special physics that are involved in being able to interpret this, but nevertheless, one can characterize electromagnetic phenomena in part as wave type of phenomena. All right, now when we look at light as a wave phenomenon, then we find the two different properties of a light wave that characterize sound waves. One, of course, is you get variation of amplitude of that wave, and you also get variation of frequency of that wave. And we interpret those two channels of information in somewhat different ways. If we look at frequency, we perceive that as color. That's our visible, that's part of the so-called visible spectrum of light. And we interpret amplitude, of course, as brightness. But if we just focus on what kinds of light that we can see, light is actually part of a much broader spectrum of electromagnetic energy. And we can just illustrate what that spectrum of magnetic energy is. You can find various diagrams like this on the web. Let's zoom in on it a bit more closely so we can see what kinds of things that we are looking at. And light, as we said, is part of a very, very broad electromagnetic spectrum. It's one of the fundamental thermodynamic properties of matter, that is the emission of electromagnetic waves. And the electromagnetic spectrum covers a vast range. We're looking at everything from radio waves, which are fairly low frequency, long wavelength types of variations, up to very, very high frequency, short wavelength types of variations on the other end up towards gamma rays. And if you look at the range of the visible spectrum, you're talking about wavelengths that are on the order of about a micrometer or so. Now, it's important to realize that when we talk about these wavelengths and frequencies, we have to be cognizant of the speed of light. And of course, speed of light is one of these constants of the universe. It's on the order of about 300 million meters per second or so. But depending upon the wavelength, that's going to vary the frequency with which the frequency of the electromagnetic spectrum. And as we said, when you're looking at visible types of light, you're talking about a fairly narrow range of the electromagnetic spectrum that is possible. If you look at the kinds of electromagnetic radiation that can make it through our atmosphere, the visible range is only a fairly narrow part of this. You can get, of course, some interesting variation down towards this end over here, and all the way down towards the lowest end of the spectrum. spectrum. But the point is that you have the same kind of variation of frequency and also amplitude in the electromagnetic spectrum that applies to sound. The major difference is that sound can vary depending upon the nature of the medium. It turns out that the speed of light is a universal constant, and it doesn't really vary all that much. Now, some more vocabulary to mention. When you're down around the visible spectrum, when you get down to frequencies that are below the range of our ability, the ability of our eyes to sense it, we're in a region known as the infrared region. All right, and so this is infrared down here. When you get up above the visible spectrum, then you're getting into a range that is known as the ultraviolet spectrum, that is above ultraviolet, and this can extend all the way up into X-rays and gamma rays, but the range at which we can actually sense light is actually quite narrow. Now, when we are talking about these other types of electromagnetic radiation, there are some important things to keep in mind here. One is that depending upon where you are in the spectrum, this carries with it information about how much energy is being carried in the light wave. The energy that's carried in a sound wave is fairly intuitive because it's a pressure. It's something that we can get an intuitive grasp for. Energy is carried in light, though, and the amount of energy that's carried is going to depend upon the frequency. When you're down in this range, right down here in the infrared range, you're talking about light that is felt primarily as heat. And this tendency of electromagnetic waves to carry heat is an indication of the kind of energy carrying property that it does have. And we'll have some more to say about this when we talk about energy budgets and especially the greenhouse effect. When you get up into this region right here, you're talking about very, very energetic light waves being propagated. So energetic that in fact it can start doing damage to molecules. You can see when you start getting up into the ultraviolet range, you're talking about wavelengths that are on the order of magnitude the size of molecules, and that can cause all kinds of interesting damage to molecules, which we can feel primarily as sunburn and those kinds of things, but which can also do things like generate mutations and those sorts of things. And the further you get up towards this end over here, the more energetic those molecules and the more damaging those kinds of light waves can be. A third thing to note about the variation of wavelength is that it is related to temperature, and this is one of the fundamental thermodynamic aspects of light. Depending upon what temperature you are at, and this is measured on the Kelvin scale, the absolute temperature scale, depending upon the magnitude of the temperature you're at, that will determine the kind of light emission that is coming from your body. When you're down here at very, very cold temperatures, you're talking about emission of light as radio waves. When you start getting up into temperatures that are close to what we are experiencing, the kinds of temperatures that exist on Earth, for example, up around 270 kelvins, 270 to 290 kelvins or so, which translates to from 0 to about 30 degrees Celsius. Then you're up into the infrared region right over here. And when you start getting up into sun-type temperatures, up around 10,000 to 20,000 kelvins or so, then you're starting to get into not only the visible range, but also the emission of ultraviolet radiation as well. Okay, so that is some of the vocabulary of the two principal wave phenomena that are important for the physics of life. One is sound, that is propagation of mechanical waves in elastic media, and the other is light, that is propagation of electromagnetic waves, and you don't need any kind of a medium for that. But the interesting thing about both of those is that they both have in common a common vocabulary. That is, they can be characterized as variations or relationships between frequency, wavelength, and period, and speed of propagation. And those relate to one another in a fairly coherent fashion. And understanding that covariation is key to understanding how these forms of energy interact with living systems on Earth. Okay, well, that's all for today, and we'll see you another time.